This is a potential divider demonstration for National 5 Physics. So first of all, the equipment. Got a battery connector, got a number of resistors, a couple of variable resistors, a thermistor, an LDR, and a component holder. We've also got two multimeters set to measure voltage and a power supply. I have set the circuit up in its simplest form with no components other than the power supply, and as you can see we're reading 6.13 volts from our DC power supply. I have now connected two 1000 ohm resistors in series across the potential divider, and as you can see we're still reading 6.12 volts. I have moved the voltmeter location so it's now measuring the voltage across here, and again, no difference. But what if I measure the voltage across just one of the resistors? So I am now measuring the voltage across the top resistor, let's be imaginative and call it R1, and it's reading 3.05 volts. This is the voltage across the lower resistor, let's call it R2, and it's reading 3.06 volts. Due to the way that they are manufactured, the resistors won't be identical, so that's why we get a slight discrepancy in the voltage. But you'll also notice the 3.05 and the 3.06 add up together to make 6.11, which is pretty much the same as our supply voltage. You should hopefully remember from earlier electricity education at school that the voltage will be split equally across components in a circuit, but that only works if they have the same resistance. So what happens if we swap one of these resistors for a component with different resistance? So what I have done here is replace the top 1000 ohm or 1 kilo ohm resistor with a 10,000 ohm resistor or 10 kilo ohm resistor. So let's measure the voltage across it. So as you can see, the voltage is now reading 5.57 volts across this resistor. And hopefully you'll be able to figure out this means the voltage across this one is now going to be far lower. So let's bring in a second voltmeter. So as you can see, whilst the voltage across R1 is 5.57 volts, the voltage across R2 is 0.55 volts. You'll also notice that if you add these two numbers up, you still get back to the original supply voltage. The voltage across here has not changed, it is the voltage within the components across this resistor and this resistor that has changed. Thankfully, you don't have to measure the voltage across the components anytime you want to work this out. There is actually an equation for this calculation, which I will now show you. If you want, you can use that equation to calculate 10 kilo ohm for resistor 1 and 1 kilo ohm for resistor 2 to see if you get similar values to what we got in the real world here. I will now give you another couple of examples to see if you can work out for yourself what the voltage should read across them. I have replaced the top resistor, R1, with a 100k resistor, so that is 100,000 ohms, and the bottom one is still a 1k resistor, 1000 ohms. Have a go with the equation, pause the video and see if you can work it out, and then I'll reveal what the real world answer is. So here's our real world figures. And for this final example, we have a 2200 ohm or 2.2 kilo ohm resistor as R1 and a 10 kilo ohm or 10,000 ohm resistor for R2. I will now reveal the figures, see if that's close to the figures that you worked out. You may be wondering, we've only worked out the voltage across this component using that equation. How do we work out the voltage across this component? If you were paying attention earlier, you would remember that the supply voltage is split across the two components. So if we know this voltage, and we know the supply voltage, then we work out that voltage by Of course, we don't always have to have fixed value components in the potential divider. We can have variable components. Here I've got two variable resistors, currently reading the same voltage, but you'll notice if I decrease the voltage of the top one, R1, which is this voltmeter, the voltage across it decreases, but the voltage across R2 increases, even though I'm not increasing the voltage across it. I'm only changing R1. If I now leave that and then change R2, you'll see by decreasing the resistance across it, I can increase the voltage across R1. And of course, if I increase the voltage, it goes the other way. Again, noting that these numbers always add up to the supply voltage. You can use variable resistors such as these to fine-tune other components in a circuit such as this. Here I have an LDR at R2, which increases in resistance as light levels drop. As you can see, put my hand over, the voltage across it increases because the resistance across it is increasing. Say I wanted this voltmeter, the voltage across the LDR, to read an arbitrary number of 0.7 volts when I put my hand across it like this. As you can see at the moment, it is only reading 0.2 volts when I make it dark. So what I can do is twiddle the variable resistor until this voltmeter still reading below 0.7 volts, but when I make it dark, it should increase to over 0.7 volts. So here we go, 0.45 volts, but I put my hand across it. It is over 0.7 volts. Take it away, drops below. Of course, we can invert this by putting the LDR on top. So now the effect is that this voltage is currently reading above 0.7 volts, and if I make it go dark, it reads below 0.7 volts. You don't just have to use LDRs, you can even use things like thermistors. This is a negative temperature coefficient, so as I heat it up, it decreases in resistance, therefore causing the voltage across R2 to increase. And let it go, and it starts to cool down as the resistance increases across it.